So here we have a microswitch. This is just a switch that's used in a lot of different applications. It is a single pole double throw switch. The common is the brown wire it's going to ground. And then there's a normally open yellow and orange normally closed. That's going into some circuitry, but in particular there's a pull-up resistor to 5 volts on both of those switch outputs. There's a 10K to 5 volts on the normally open, 10K on the normally closed. We've got scope probe 1, the yellow probe down here, connected to the normally open. So right now that would be at 5 volts, and we can go up and look at the oscilloscope, and you can see that it's at 5 volts. And when I press the button, it goes to ground. When I release the button, it goes up because that's the normally open contact, so it's pulled up by the resistor. When I close it, it gets connected to ground. Now let's just take a look at that transition from high to low. I'm going to change the scope to single sweep. So what the scope is doing is it's just sitting, waiting for that signal to go from high to low. And so when I press it, it goes from high to low, but notice this T up here, that's the trigger point. So we're coming along at 5 volts. I press the button, we drop down to ground, I hold the button down, but we come back up to 5 volts, we go down here, we come back up, we go down, we go up, we go down, we go up. In fact, we're right now on 200 microseconds per division, and if I move our horizontal position over so that we trigger right at this point, we have 1, 2, 3, 4, a little over 4 divisions, so that's 800, a little over 800 microseconds that we're bouncing back and forth, and this bouncing is the mechanical contacts within the switch. Take a look at that one more time, go back to single slope, I press the switch and hold it, and you can see it goes down, the contact hits, the movable contact hits the fixed metal contact here, pulling the signal to ground, but then it bounces, so the pull-up resistor pulls us back up for 100 or so microseconds, and then back down for a short period and back up, and we get these bounces until finally here we go 1, 2, 3, 4. This is over a millisecond before this finally settles down. Now I have this signal going into a set reset flip-flop. The set reset flip-flop consists of 2 NAND gates cross-coupled. We've looked at that before. I have this input, and I actually also have the normally closed input going into the reset input of the same flip-flop. That's also active low. And I have channel B of the scope on the output of the flip-flop. But the important thing to remember about the set reset flip-flop is that it gets set when the set goes to 0, and it doesn't get reset until the reset goes to 0. So let's turn on channel 2, go back to single sweep, and I'll press the switch. All right, once again, the yellow is what's happening at the output of the switch. It goes down, contacts ground, pulling the 10K resistor to ground, but then it bounces back and forth. But the output of the set reset flip-flop goes up the first time the set, and it's actually set bar. So set bar goes to 0, asserted. The output set goes high, and it stays high, and it will stay high until the reset is pressed. So if we go back to auto mode, button not pressed, pressed and held down, released, pressed. The yellow is the output of the switch. The switch is going low when I press it, so the output goes high because the flip-flop is set. When I release the button, the yellow gets pulled up to 5 volts. That isn't causing the output to go low. What's causing the output to go low is the other pole of the switch is pulling the reset low, and that causes the output to go back too low. And once again, if we just look at a single sweep, we can see that what's happening is we're getting lots and lots of bounces, but the flip-flop catches the first one and stays high until the reset is asserted when I release the button, and the normally closed side of the switch goes back to normally closed.